Hello, everyone. Welcome to Cybernetic Systems Design and Dynamics Learning Activity 5 System Modeling and Simulation. We'll have another short lecture today. We'll jump into system modeling and the differences between system models, dynamic models, as well as system architectures and how those all interrelate with each other. So it'll be a bit of some systems engineering that we'll talk about today. And then we'll jump over into the lab for this week, which will cover Sage modeling. So without further ado, let's jump into system modeling and simulation. And first up, we're going to talk about what systems modeling, or sometimes just system modeling, is. And system modeling, it's heavily comes from systems, just systems thinking and complexity sciences. And I know we've talked about that to a certain extent already. And systems modeling is an interdisciplinary aspect of what it is that we're covering in this course. And when you look at system modeling, it's a tool within the systems engineering field. So learning how to do good system modeling is it's part of the job, and we all do a little bit of, especially if you're in any type of STEM field, whether you're a software developer all the way to a mechanical engineer, to even a musician. Everyone's involved in some kind of systems analysis. You may not always be involved in some kind of systems engineering, but we're always in systems curating, right? We're curating our systems, whether it's a social system we're curating. When you make a friend or you network, that's curating your social system. That's a form of systems engineering. Now, it's a social systems engineering approach, but that's kind of on the social side of it. But when we create artificial constructs like computer programs and hardware and graphic cards and CPUs, and we create airplanes and airframes and automobiles and trains and you name it, right? Those are all systems, right? They require subsystems and then smaller systems to make those the bigger system run. So when you look at systems modeling, it's a form of taking an abstract concept, conceptualizing it. I'm sorry, rather taking a physical concept and abstracting it into and conceptualizing that system, whether it's an engineering system, a computer system, a business system, you name it, we can model it. And a lot of times there's an architectural framework that comes along with this, and when we a model is part of a architectural process. So a systems architect will employ system models, right? And so think of that as kind of the bucket, right? System architecture is the big bucket, and then I put models within that bucket to create a broader systems architecture. So architectural modeling is bigger, right? It's like I was just saying, a bigger bucket. But it's usually done because it is a bigger bucket. You'll have domains. There's domain specificity as it relates to architectural models when done properly. It doesn't always have to be done that way, but it should be done that way. So you'll have an operational domain, a system domain, a network domain. You'll have a data domain for those that are like network administrators or have done network administration, like the OSI layering, right? OSI in terms of the transport layer within an Ethernet, that's a domain, right? There are different layers even within that. There's social domains, there's physical domains, there's just so many different domains that you can add to this, but there are typically some 4 or 5 generic domains that have been created through what's called DODAF, or Department of Defense Architecture Framework. It's a very good framework. We actually use it in Cyber 603 Integrated Systems Architecture. So if you've taken that, great, you're familiar with it. If not, we're coming up on it, and you'll learn more about it. So this is a good preview to DODAF. There's also another one that goes on to it. DODAF is what I call an artifact-driven framework. So it helps to classify and categorize and create architectural artifacts and help you to um, categorize those artifacts in different ways. Then there's another framework that's more process driven. It's called TOGAF, the Open Group Architecture Framework. So one is process driven. In other words, it talks about how you should go about the process of being an architect and what you should do and how that looks, right? It's a systems lifecycle approach to architecture. And then the DODAF framework is an architecturally uh, um, uh, it's an architectural framework focused on the artifacts that support TOGAF. So that's the easiest way to say that. But again, I don't want to get too far into the weeds on that because I want to focus on the system modeling and simulation, kind of just whittle it back down. I just wanted to go broad for you with you for a sec before I jump into the dump on you the some of the stuff that we're going to be doing here. So why do we even bother architecting? Why is it even something that we get into? Well, when you look at systems engineering as a life cycle, INCOSE is the International Council on Systems Engineering, and they define six generic life cycles. Six generic life cycle stages. These actually apply to project management life cycles as well, different styles, right? Whether it's an agile, whether it's a scrum, whether it's Kanban, whether it's spiral, whether it's waterfall, whether it's pairwise programming, you name it. There's a lot of different life cycle strategies to organizing work. And systems engineering helps with not only structuring the work, but understanding the integration points, the interstitial integration points between systems. So it's kind of a twofold approach when we talk about systems architecture. So it's not only kind of layering in the different domains as it relates to the architecture that you're building, but it also has to do with the life cycle, operating within the life cycle that's been established within the systems engineering discipline. So architecture happens early on. So typically it's your second step or third step um, before entering into a large project. So for example, you'll do some planning, and then after that planning, you do some human resources mapping, and then you get your people, you get your time, you get your budget, you establish all those pieces, and then you say, hey, what's my architecture going to look like? I get my use case requirements, I get my functional requirements, I get my non-functional requirements, and then I go into architecture, and then I build out architecturally what it is that I'm envisioning. You do a current state analysis, and then you do a future state analysis, and then you say, hey, I'm going to pull that all together. And then when you figure that all out, then you get into detailed design, which is kind of architecture and design aren't the same thing. So then you'll kind of go into your breakout rooms, and then you'll do design for your subsystems. And then after you've gotten your design out of the way, then you get into implementation. That's where the rubber meets the road. You get your developers, you get your engineers, they come together and they say, hey, these are the requirements, this is what I'm marching towards, and this is what I'm going to build. And then you get into test, validation, verification, and then you do operational field testing, and then there's operational verification and validation, and so there's all these different steps. So really complex architectures follow what we call this V model, graphical V model. And I would highly encourage you to kind of understand and if there's anything that you take away from our design and dynamics course is that it's really a systems engineering course, and that's what this is. And so with a little bit of simulation that we're going to be doing. So now that you've kind of got a feel for that, let's go to model and architecture and the couple. Let's run through some terminology. So from a terminology perspective, there's system model, which I talked about, system architecture, but there's three more things I want to talk to you about, which is this idea of a static model versus a dynamic model. And then I'm going to reintroduce system dynamics. So a static model is like it sounds. It's a model that is a model is static when the system model is not in motion. So what's a dynamic model? Well, it's the opposite of that. It's when a model that is in motion is dynamic, and that is that it's a dynamic model is in motion. there's different levels to that. There's different ways that that works. And I will be able to illustrate that with you this week in a lab. So in our lab rather. Okay, so last up is system dynamics. It's a system model that is in motion. So that's what it is. It's taking your system architecture, you're taking a portion of that, you're taking a model, and then by itself, the model is static. But then after that, I can make a decision, and I can use some tools to make a dynamic model, and that's what we call a system dynamic. And so now there's another version of this that I want to be clear on. When I say it's system dynamics, I'm thinking about it from a much broader perspective than what the official terminology is for system dynamics, which is kind of more isolated stocks and flows and organizational views and ecological views. A dynamic system or a system dynamics of that system, it can represent anything. It just doesn't, it's not just focused on organizations and stocks and flows and inputs and outputs. And those are all important, of course, but it's broader than that. So this brings us to simulation. We are going to run, I'm going to teach you what it is. And a simulation is essentially taking a model and then making it dynamic. That's what it is. It's simulation is a bunch of models, one model, a whole bunch of models put together, and then you push play on it. But to do that, you have to make it time variant. And you have to have variables that are bound by time. So not all variables are bound by time. And it'll make more sense once we pull this together. Because you'll be like, well, aren't all variables bound by time? No, that's not true. And there are variables, actually there's quite a few that aren't bound by time. Now, I'm not trying to get into an existential conversation that, of course, we live in a universe where everything is bound by time. Of course, that's true. But certain concepts within a model, they stay static and they don't have any input and output. And the way we drew them up conceptually doesn't have any input and output. And then they're not cybernetic, because cybernetic is all about a change, all about a difference, right? The fundamental concept of cybernetics is that there is a change, right? There's the idea between an input and an output, and there's a difference. I can have an input and an output, and if I put something in and there's no difference on the output, then that means that there's no change. And so to a certain extent, it's time invariant. And so there are we aren't going to be dealing with that. I'm going to make it real simple. We're going to do a simulation that's going to be pretty straightforward. And we'll jump into that here in just a minute. So to clean this up here and finish up and put a wrap on our lecture, let's talk about some of the things that we're going to do here. There's Sage Modelers, what we're going to use this week. You used Loopy last week. It's similar, but Loopy is a very Loopy's kind of cool because you can turn it on and just let it go, right? And then you can see the behavior of the nodes and the relationships. But there isn't a lot of granularity, right? It can approximate large systems, but you kind of have to tweak with it and goof with it, and you probably played with it for a little while. And please do play with the Loopy software, because part of your project is to demonstrate either the Sage modeler or the Loopy modeler in creating a dynamic model as part of your group project. Do not forget that. You must create a Sage model or a Loopy model that is dynamic as part of your output for this course. So your group project, make sure you have a very good dynamic model, because that's a core part of what we're doing here, is learning how to think in a dynamic way to create a model and then make it dynamic. Okay, so similar to Loopy, but there's a lot more granularity. So we'll run through that in the lab. But so to wrap this up, we've got a simulation lab, and we're going to do basic principles. I'm going to go through and show you the basic principles of just positive inverse and a non-relationship, and then a model evaluation. What you want to be thinking about, and this has applicability to machine learning as well, when we do model evaluation or AI model evaluation, we always ask, do the relationships make sense? Does the model make sense? Are the variables making sense? Is it actually a good approximation of what's going on in the real world? Is it a stable model? Under what scenarios is it stable? And we ask this question. So as grad students, this is a word you need to get comfortable with: is generalizable. How generalizable is my model? How generalizable is my research in general? And when I say that, I mean what that means is how far and how expansive is my research. Okay, that's all I got for our lecture today. And with that, I will see you in the lab.